Hi, this is Martin Eder from DTU Wind Energy, and I would like to take the opportunity to introduce to you a brand new course which we will be running at DTU Lyngby in the fall of 2020. If you share our fascination for the world of metals, how metals behave, and how we can improve metallic components that make up a wind turbine in order to make it more sustainable and to reduce the cost of energy, then the course Metal Structures and Components for Wind Turbines might be ideal for you. It is interesting to see how many different materials we can find in a modern wind turbine. We have the fiber composites making the blades, but we have a lot of metals comprising the support structure of the turbine and also all the parts you can find in a nacelle, such as bearings, gearboxes, and so on. And we also have some concrete, which is mainly distributed in the foundation of a wind turbine. But looking at the weight percentage distribution, we see that over 80% of the mass of a wind turbine is steel, followed by other materials and metals such as copper and aluminum and rare earth metals, mainly part of the generator and other parts in a nacelle. But looking at the predominant presence of metals in a wind turbine emphasizes the importance of the role of metals. And this gives the motivation for this course to cover all the important metallic parts in a wind turbine from a structural engineering point of view. The course covers a wide range of different topics, and we try to make them as interconnected as possible. Now, in our course, we split it into different modules. Each module is dedicated to a specific topic or an aspect of a wind turbine, such as the support structure, the monopile you can see on that slide, or the tower, how the different tower segments are joined together by bolting or by welding. And we also cover generator technology and gearboxes, as you can find them in a nacelle. Now, we put a big emphasis on this course in teaching the concepts rather than memorizing specific equations. So if you look at the course overview, we start with the properties of steel from a very small scale of an atom, and then we move our way up to bigger and larger scales until we arrive at macroscopic level, and then we look at loads, where loads come from and how loads affect the structure. We look at the tower itself. We also look at fatigue from a materials point of view and how to use that information to model the fatigue life of a structure. We cover bolted joint connections, how to make them more durable and increase the fatigue life, but also the welding process in terms of residual stresses and change of the microstructure and how that affects the performance of a material and how we can model welding processes. A very important topic also is corrosion, and we start with the electrochemical concept, and then we continue to look at corrosion models and how they can be used to predict the lifetime of a structure subject to harsh environmental conditions. We also cover generator technology, for example, also superconducting generators. And a part of that is, of course, magnetic materials and how to recycle magnetic materials and the rare earth metals we want to extract from them and to reuse. And then we have a specific topic dedicated to bearings and gears and gearboxes, where light is shed on effects such as white edge, cracking, or wear effects. Towards the end of this course, we also have guest lectures from DNVGL, Ramböll, and Ørsted, presenting their view from a real-world consideration to you, so that you can then relate the course content to the real world outside in the industry.
During the course, we will go through the basic mechanical properties of steels and see how these properties are the limiting factors that affect our design choices for the turbine. Since the curriculum is specifically dedicated to wind turbines, simplifications will sometimes be necessary to demonstrate a specific behavior. That being said, we will go into depth on topics that are of particular importance for wind turbines, such as fatigue in metals. Gearboxes are one of the most vulnerable parts of a wind turbine. A gearbox has a high failure rate and is an expensive component in itself. Failures will also cause long turbine downtime as it's difficult to replace. You need a big crane, good weather, and if it's offshore, you also need a big ship. Around 75% of gearbox failures are estimated to be in the bearings, and about 75% of the bearing failures are estimated to fail due to the formation of subsurface cracks called wide edging cracks.
Now, if I asked you to separate a paperclip without the help of any tool, how would you go about that? Exactly, you would bend that paperclip open, and instead of pulling it apart, which would be almost impossible to do without some tool, you will take it and wiggle it backward and forward until the paperclip breaks. So we can see that a material can break subject to cyclic loading conditions at load levels which are much lower than the strength of the material. And we are referring to this effect as to fatigue. And in fact, fatigue is the most prominent failure cause we find in wind turbines. And it can lead to catastrophic failures of the entire turbine, as you can see on that slide. But also fatigue in general has led in the past to severe incidents and also fatalities. It is a very insidious failure mode, as usually the fatigue crack initiates and propagates over a very long extended period of time, largely undetected. And when you detect it, it is usually too late. So because of this insidious behavior of this failure mode, we have dedicated an entire module of this course to high cycle fatigue. You will learn how to see and identify a fatigue failure by looking at the fractured surface, what the characteristic elements are. As an engineer, you need to know to identify the root cause of a specific failure from a materials point of view, but we will also learn how to model the fatigue in metals and how to use those models to predict the fatigue life of the component. And ultimately, we will teach in that course how to use your engineering judgment to assess the fatigue life of a structure, and maybe also to improve the design of a specific component so that it can live up to its designated design lifetime of 25 to 30 years. It is rather difficult to pull a sheet of paper apart, but it is comparatively easy to fold a sheet of paper together like that. We refer to this phenomenon stability failure, which pertains to structures or components which are subject to compressive stress. Now, if you have ever stepped on an empty beer can, you will have realized that once the can starts to fold, it does not offer any resistance anymore to the force you apply with your foot, and it just continues crashing until it is very flat. And this on the slide, you can also see, can be used to crush an empty beer can on the forehead without injuring yourself. And if you have ever asked yourself why this is possible, then this course provides you with a theoretical background to mathematically formulate the very interesting phenomenon of cylinder shell buckling. And this very phenomenon also occurs naturally in the tower of a wind turbine, which, if not properly designed, you see on this slide, leads to a catastrophic failure due to local buckling. In this course, we will not only look at the foundations and the mathematical source of this phenomenon, but also look into more practical ways of using numerical methods to predict the buckling strength of a tower, and also to investigate the pre- and post-buckling behavior of a tower. Now, in this course, you will learn what the significant parameters are from a designer's engineer's point of view to prevent buckling from happening and to design wind turbine towers that are strong enough to sustain peak loads without buckling occurring.
Hi, my name is Asger. I will tell you something about neodymium iron-boron magnets and why we use these neodymium iron-boron magnets for generators in some types of wind turbines, and especially some type of wind turbine generators. And so besides from just telling you about this exotic material, I will also tell you the sort of how to recycle the neodymium iron-boron magnets and how this is currently done. What you see in this picture is kind of a big turbine that was decommissioned, so the magnets were taken out of the generator, and then this is what you can see at your top right. And now the question is, of course, what do we do to these magnets after the turbine has stopped working or come to the end of its lifetime? At the bottom picture to your right, you can see the size of the neodymium iron-boron magnets is 10 by 10 centimeters, and that they are 2 centimeters tall. These magnets are very strong, so we need to take care when they're taking out. And in the lecture that I will give in the course, we will be discussing the fate of these magnets further on.
Hi, this is Ali Saradi from DTU Wind Energy. I will cover the corrosion part of this course. As an example, economic loss of corrosion only in US is around $270 billion per year. For wind turbine, corrosion reduces the designated lifetime of the support structures. Therefore, corrosion protection is very crucial for wind turbine support structures. In this course, you will learn the basic concept of corrosion, how to calculate corrosion rate and corrosion potential. You will get familiar to different corrosion type. You will learn about different corrosion protection system, such as galvanic cathodic protection that you see in the picture. And at the end, you learn how to use design standard to design a suitable corrosion protection system for a wind turbine support structure.
Now to the course details. It is a 5 ECTS course at master level, and it will be held in autumn on Tuesdays between 8 and 12 on Lyngby campus. In terms of grading, the overall grade is split into 3 quarters, making the oral exam, and into 4 hand-in assignments, making 1 quarter of the grade. These 4 hand-in assignments will contain some practical calculation exercises pertaining to the models and concepts introduced in the lecture. And these examples will facilitate deep learning rather than number crunching. And they will also be furnished with some concept questions where a deep learning approach is used to make sure that the concept of the models is understood. Now for the oral exam, we will look at your presentation skills and your engineering competence to engage in a scientific dialogue in a friendly atmosphere between you as an expert and us as an expert, with a topic that you have randomly drawn from a pool of our 13 modules. And also, the second part of the oral examination will be Q&A sessions that pertain to your handed-in assignments. Now, if we got your attention to sign up for this course, please do not stop and hesitate to do so immediately. And if you have any friends or colleagues you think might also be interested in participating in this course, also spread the news, please. We are very interested to get as many students signing up to this course as possible. And finally, if you have any questions regarding the content of the course, please do not hesitate to contact one of us. We would be very happy to respond to your inquiries in a timely fashion. And at this point, I would say thank you very much for your attention, and I hope to see you very soon in my lectures. Now, high quality teaching is very important to us, and I think the advantage of this course is that we are very versatile. We are sharing the lectures between 4 lecturers. I myself, I'm a civil engineer, but we also have a material scientist, Hilma, and we have a physicist, Aska, and we also have a mechanical engineer, Ali. And I think the strength of this course is that we can therefore cover a wide range of different topics. We try very much to interlink the different topics as they are connected in practice. And also not only purely focus on the theoretical framework of all the different modules, but also enable the students to connect them to the real world outside so that the students can apply them in practice when they work for industry. Now, in our course, we have a part that of course covers the theoretical aspect where we will use equations and also differential equations and other means of describing the foundations of the curriculum. But also we will use experiments conducted in the lecture, which are corroborating and supporting the theoretical concept so that we can trying to falsify the theory. And those are tabletop experiments such as bending experiments or drop mass experiments to investigate the plastic behavior of structures. We are, of course, also issuing questionnaires to students to assess our course. And on this slide, you can see an excerpt of such an evaluation. And we can be proud to say that the majority of students was very happy with how we conducted our course. And of course, there are also always regions where you need to improve, and we are working very hard on those things where we scored low to improve them in the next round. And we hope to get you as one of those students who will hopefully also be fully satisfied with that course and get the impression that you have learned something useful.